So thank you, Mario, for the nice introduction, and thanks to the Nano-Tera organizers for giving us the chance to present here today the objective of YINS. So YINS actually stands for a completely different meaning, pretty unclear for almost everybody when we started. I hope it's clear at the end of this presentation. So the idea is that we want to optimize the energy utilization in future data centers. So basically the acronym YINS, it's after long discussions in the consortium we came up with this, which is a slang word from English, from the Pittsburgh region. It means you all together. Basically, like when you go to the cinema, in this case, we're trying to fix a big problem all together. So this one is a project that involves also quite a lot of partners because indeed, like a Nano-Tera project, we try to go from the nanoscale to actually optimizing circuits and systems from next generation computers to really the fully Tera scale, where we actually try to address the system level management for complete data centers. So the idea here is that we have expertise at multiple levels. So it's a multidisciplinary consortium where you have people from ETHZ and EPFL, so 6 laboratories in total, as well as 3 main industrial partners, covering also different aspects of the data center design and integration process. So the project motivation starts from the widely accepted observation that IT, information technologies, are actually as a pillar of the current modern society. So they have become a really indispensable element in developed countries to create knowledge. And knowledge in the end becomes culture and money. So in that sense, what we actually have here is a way to develop the society, and this is due to the creation of a new centralized processing paradigm where we are trying to create science at the same time as efficient services by doing centralized processing, centralized computing. So the idea here is that when we have a look at the current design of data centers, we notice that this evolution has come since 2005, and the consequence of starting developing IT for our society has resulted in a dramatic increase in power density utilization for IT services. So you see here that right now we're at the border of IT just providing basically the same amount of energy needed for 50 million Swiss houses in the US, and the sense that every time that you build a large data center, and we hear some in the media, you see that it's a huge investment, it's a huge size, it's a very complex process. Unfortunately, not only is just the one-time investment of this large budget, but it's actually power is actually consumed more often and overcomes the initial cost for developing the data center. This is extremely important for countries like Switzerland, where service-based products and development is actually more than 50% of the value that is provided to the society. So in that sense, what we try to address in this project is the fundamental issue, which is how to design effectively these data centers with a minimal energy consumption. So you want to not just have extremely high performance systems that you can do a lot of computation in data centers, but you want to do it consuming as minimum as possible energy. So you want to really make it energy efficient and friendly for the environment. Why can industry fix that? We have seen that there's a lot of effort being developed in this area for IT vendors, and there are many partners that actually work into this area. The main issue that you have, if you look at the whole spectrum, is that typically these vendors are targeting individual layers of the whole design process of a data center. And there is nobody that really targets the whole data center, except if we look at the recent exercise that is done by the big cloud operators like Google, Amazon, Facebook, where we hear very often that they are doing a lot of efforts on reducing the energy that goes into the center because it's money that they spend. But the main problem with this type of exercises is that they are doing it and they drive the market, but they only optimize their own technologies. So it's not an open technology for everybody. So you cannot do that if you want to use this in your own company, in your own data center. So what we are trying to do here is to completely revisit the way that is actually done to create these data centers. We want to really look from the ground to the complete design of the data center and optimize all the layers, from low power circuits to complete cooling infrastructure, looking at the whole server room and data center architecture, and provide complete thermal management strategies of the whole data center. So this requires, as I said, something that fits very nicely in the Nano-Tera framework, because we are looking really from extremely small components like transistors and architectures for power, for computing systems, to the full Tera side where we actually optimize the whole energy consumption of data centers. For doing that, we have partners that come from mechanical engineering, computer engineering, and computer science, looking at the different problems. And at the same time, we have 3 industrial partners that are the ones that provide the experimental setups: BrainServe, Credit Suisse at the full data center level, Eaton at the level of infrastructure, and we have 3 additional startups that are providing innovative technologies for energy recovery and circuits. So overall, what we expect at the outcome of this project is to provide a plethora of technologies that can work all together to make sure that we can pass from the typical examples that we hear today of full data centers of these big vendors being optimized and being very well optimized for a metric that they very often you will hear on the media, which is PUE, which is power utilization effectiveness, which is how much energy is really used by the computer and how much energy is used by the infrastructure. So you hear very often that we are close to 1. Basically, you don't use anything on the infrastructure. But if you look at many of the companies that exist in Switzerland today, they don't have this, but they have something like this. And this, I can tell you that the power utilization is not 1. It's very far from 1, but we believe at the end of this project we can make everybody become 1. And that's the main target of this project, to make sure that we can do that, and eventually for the environment, IT will not become a burden, but will be actually something that will be scalable and energy efficient. So thank you very much.
Yes, good afternoon, ladies and gentlemen. So as you've seen on the data center, it was a shame there was no solar cells. And of course, you need to provide all that energy. And this is part of the Synergy project I want to present you now, where we will discuss a little about photovoltaics and application. So what are we addressing in this project? So the title of the project, Synergy, means that we want to go for a system for ultra-high performance photovoltaic energy harvesting. And we have just started a few months ago this project. And we address 2 types of markets that are quite different, but I will show you why in the device sense they are very close. On the one side, for photovoltaics, if you want to go for large area electricity production, you need to have solar cells that are even more efficient. And today's solar cell, you need them cost affordable. You want to be able to cover large areas, and of course you need very high reliability and lifetime. So that's one kind of application. On the other side, we have the energy scavenging problem or opportunity, and I can tell you that more and more people are thinking of putting more and more solar everywhere. And here, of course, you also are very happy if you have very high efficiency. You are happy if you are able to adapt to wide dynamic range, because you can quite often work in an environment where you have only 1 part per 1,000 of the sun, or 1 sun. And then this is a lot of requests on the electronics that comes behind the solar receiver. And of course, here you don't need to guarantee 25 years of lifetime and to withstand the hail that could come on the roof. And the very nice point about photovoltaics is that indeed you can do these things, you will see, with one kind of, or several kind of technology we have on board. And the why of working on these topics, or for Switzerland, of course, we have the electricity issue. If we need more and more for the IT, we have a limited space available on the roofs, still quite a lot of space, but the higher the efficiency, the better. If you want to stay innovative and competitive on the photovoltaics market, you need novel approaches. And we have seen that electronic devices are more mobile year after year, and you need specialty devices. And if you remember your studies, you would remember this diode equation here. It is a diode equation for a solar cell, and you see the famous exponential increase of the current with the exponential factor here, and the current saturation density is a G0 factor. And the very nice point about this equation that it tells you that if you want to make a very good solar cell, you need to have no shunt, no parallel resistor, which is represented by this RP here. This is obvious. But you also want to have this G0 factor as small as possible. And this is the best solar cell you would get for terrestrial application. But the nice thing is also that if this G0 is very small, and you get that mostly by having a high band gap, then you are able to have a solar cell that works also very well at low illumination, better than any other solar cell. And in a sense, and you can just see on that graphic, that you can have solar cell that even at 100 lux, that means almost much less light than in this room, you can still have quite high voltage. So this offers some opportunities in the sense that if you're able to make high band gap cells, even possibly put them on low band gap cells, you are able not only to scavenge a full solar spectrum, but you are able to have devices that will grasp in indoor environment as much light as possible. And this brings us to the topics we proposed for this project, which was first really focusing on making a next generation of devices, and these devices are complex systems. And what is the story about? Well, in Switzerland, we are lucky enough, we have several groups of researchers that can do fantastic solar cells. You have the group of Ayodhya Tiwari at EMPA, who can do some of the best chalcopyrite solar cells. CIGS can do telluride solar cell. You have the group at EPFL in EMPA and CSEM in Neuchâtel, who can do high efficiency crystalline silicon solar cell, which are excellent in the infrared. You have the group of Michael Gretzel, who can do high bandgap perovskite solar cells, and other groups are also starting in Switzerland on that topic. And you have also innovative approach with making like gallium arsenide and nanowire high bandgap solar cells. So if you would be able to combine the best high bandgap solar cell with the best low bandgap solar cell, then you would have a potential to reach solar cells efficiency that would be in the range of 30%, so around 50% higher than the current product you can find on the market. And also you would have devices that are particularly good in energy scavenging. So this is basically the goal of this topic. So it just started. You can see a few posters. We have already made the first coupling, filtering one cell with another cell. So we are having the first results here. And really the goal is to be able then to realize the first devices and then to couple that to some electronics to power something and to see what is the potential for a large system. And in order to realize this project, we have the network that I've shown here, and with various interests as well from the solar side, as for also from the industry side in the microelectronics. EM Marin and Azulab are also our partners in this project. I thank you for your attention.
So if you'd like to use this panel, photovoltaic panel, you need to introduce this one into a grid. The grid should be smart. So this project is about the smart grid. So to address such issue in the society today, how do we handle this stochastic energy, and how do we live in a building where this building should be as smart as possible, and then how do we feed back all of those data to the people inside this one? So this project, in fact, is addressing this topic. Starting with the consortium, I can show you the people involved in this project. We have 3 labs from EPFL with the HES in Sion, and 3 companies, Romand d'Energie, as well as startup eSmart and National Instruments. So let's go in the different layer of this project, starting from the S-cube, S and S, smart grid, smart building, and smart sensor. So smart building, the challenge is speed and speed and speed. Smart grid means real-time monitoring. We have this photovoltaic panels providing energy, and we have other sources of energy, and we have to deal with those data, managing our grid and let this grid be efficient. So we need to monitor everything, starting from detecting the power consumption from building, dispatching those data, and being capable to emulate the state of this grid. So if we move now to the way of communication between this network is ICTs for sure. Secure, performance, so this layer of ICTs is mandatory, and then again, times is important. I'm speaking about speed. We are about the millisecond to handle a huge area of buildings such as the campus of EPFL. I have to mention that this project is applied to the campus of EPFL. We have some buildings, and you can visit outside the poster site to see an example of the building of EPFL, measuring the power and seeing how that those data are communicating, and then seeing as well the building inside, the behavior of offices of some of those buildings. Now, what about the control? The control is demand side. So when the grid need to control something, the building should react. Mean that the demand side, when we ask you to reduce the power consumption for a given reason, so we have to manage this one. It means the second layer is smart building. Now what about you? Ladies and gentlemen, you are inside those buildings. You are not going to switch off the light. So we have to provide you with a different layer. Provide you with the sensor. One of the aim of this Nano-Tera is sensing, dispatching data, and giving those to people inside the building to be capable to manage their own environment. So this is the last layer of it, when the human living, or the person living in this kind of building control from the top down, can get some bottom up and try to improve his own power consumption. So to do so, let's go not a long time in the technique. You have plenty of time to see the demonstration outside. The active distribution network control is an important word, ADN. It's active, means that you are measuring over all the time. And this is done by phase measurement unit. At medium voltages, building in EPFL, you can check it outside, is measured all the time. And then we detect the phase, we push those phases toward the data place where those data are collected, and this is done by ICT layer. And then when you arrive to this one, we are able to control and to protect. And this means that the state estimation of what happens should be all the time monitored. We have to absolutely understand if this is normal, if what happens is normal with this huge amount of data we receive, or we need some emergency decision. So we need to filter out those data and to arrive to a decision that our data fit well with the normal smart grid or ADN functionalities. Now we arrive to the ICT. ICT is not only for sharing data for email between people or Facebook environment, so we need to have some specific ICT for energy. It means that this layer is absolutely mandatory for mainly two reasons: speed, then the second one is security. So it means that we cannot let everybody have a look on what happens inside, and then how do we manage this one. And the last one is your own place. Ladies and gentlemen, you are inside. What about controlling this one? So it means that electronics development in this project is targeting to replace plugs, the wall plugs, by a specific one with a specific IP that is capable to create a cluster of kind of loads to be controlled either by yourself or by the grid. For inertial load, for heating and cooling, where we can save or control a big amount of power, it could be done by the grid from time to time. And then some of them is your own environment light, some specific control of the heater or the cooler, are clustered together with a kind of electronic collecting those data and managing. It's a kind of Internet of Things where components could communicate between themselves. And then this is done with adding this kind of sensors, because you are living inside and you have to control your environment by a smart way as well as by your own decision. Thank you.
Good afternoon. I'm John Lygeros from ETHZ Zurich, and I'll present the project HeatReserves. It started about a year ago, and I won't have any results about the project, but I'll just give you the great context in which it lives. This is one of the systems projects that were mentioned in the introduction, and it deals also with buildings from the energy consumption perspective. There's some rough statistics here. Buildings account for a large fraction of the energy that we consume in Europe. Much of this goes into climate control, ventilation, heating and air conditioning. And people have been looking into how to improve this to reduce improve HVAC, improve climate control to reduce the consumption, energy consumption of the buildings. So the aims is to increase energy efficiency, but at the same time maintain user comfort. And generally people use weather forecasts for planning and then taking into account forecast uncertainty to minimize energy. So it's being a control engineer, I think of everything as control loops, and that's a control loop. Here you have your building, it's affected by the weather. You have measurements that tell you about the efficiency and the user comfort of the building, and then you use weather forecasts and occupancy forecasts, how many people are in each room at any point in time, and a computer to just figure out what to do with the building. And that's actually an interesting control problem. There's many challenges. The buildings are relatively slow, so if you want some action out of them, you have to think about it early, think at the beginning of the day what you'll do for the whole day, for example, plan. So you need sophisticated control methods to do this. There's a lot of uncertainty about occupancy, about weather forecasts, sometimes about price of electricity, depending on which market you're exposed to. And this makes it a very challenging control problem. And many people have looked at this, and it's a very active area of research. What HeatReserves builds on actually is, or looks into, is the connection of this picture, how do you control buildings to improve their efficiency, with the grid. This is a one-slide crash course into sort of grid and what it looks like and what it might look like. I stole 3 graphs from a talk by Tariq Samad from Honeywell because they perfectly reflect what I want to say here. Traditionally, you think of the grid as demand being inflexible and uncertain, so it has to be served. If you put the light on, the light goes on. And from the point of view of the grid, you don't know exactly what the demand is going to be, so there's some uncertainty around it. And you compensate for that by controlling the grid itself, so by controlling generation. So there's a feedback loop that measures, for example, frequency deviations, voltage deviations, and so on. And given your uncertain load, this could be your building in this project, you have to decide how much to generate, and then through the transmission and distribution network, give it to the load. And this basically, the generation side is responsible for picking up all the slack. Now, as renewables are coming into the picture, you start getting inflexible and uncertain supply. For example, photovoltaics or wind production. You don't know exactly, you have a forecast, but you don't know exactly what you're going to get at any point in time. You schedule reserves for this, and you have to account for this, any mismatch from your schedule as you go on. So now you have question marks both on the load side and on the grid side, and one of the concepts that's being put forward for this is sort of demand response. So who's going to pick up the slack? Now both generation and load are uncertain. You put a second feedback loop where the uncertain generation asks things of the demand. So you reduce your demand or you increase your demand depending on how much energy is available. What exactly goes here? There's a dollar sign there, meaning there could be prices, but this is not the only thing out there, so there's many concepts about how to do this. Okay, how do buildings come into the picture? Buildings store energy, in a sense, and they store energy in terms of thermal energy. So there's some capacity in a big building like this, where you can sort of heat it up a bit or cool it down a bit, just small amounts, but then consume a lot of energy in the process. And also, if you think of big populations of very small loads, like in our homes, we all have gadgets like water heaters and air conditioning devices, heat pumps, and so on and so forth. All of these, you can also store energy in some sense. You can use it to store energy by increasing the temperature, for example, in your water heater. So the idea is to use this for doing demand response. Somehow the grid asks of the building something, and they reduce or increase their consumption to accommodate. So then the point is that they will have to suffer for this. If they're highly optimized, they'll be a little bit suboptimal to accommodate this request, and they're going to sell this slack to the grid and be compensated for it in some way. The aim is to facilitate the introduction of renewables. So you have some, if you have uncertainty on the generation side, you accommodate it by changing the demand. And that's actually an interesting topic because there's a lot of engineering issues in play. Classic building climate control that I alluded to in my first slide. Also things like when you have many small loads, okay, one water heater won't do much for you, but 10,000 would. So how do you control these 10,000 water heaters without going to each one and say, you do this, you do this, you do this? That's too difficult. So how can you control the whole population by macroscopic signals? We heard also in the previous talk, there's communication requirements. What information do you need? What information do you need to convey back, and so on. And at the other side, there's also economic issues. How much is this worth to the grid? And how much do the consumers lose when they offer this service? And then if you want to somehow compensate them, what kind of market schemes do you need to put in place to convince people to participate in this? And finally, there's issues involving privacy, for example. Why would people tell you what they're doing, and how much are they willing to divulge, and so on and so forth. So to address this problem, we put together a consortium that sort of covers the basis on this. To do this, you need some power systems expertise, and that's the power systems lab at ETHZ, my colleague Göran Andersson, who's looking into this. You need control systems, and that's what our lab is doing, automatic control lab. Then you need someone that knows about grid operations and how much reserves are worth to the grid. That's SwissGrid is one of the partners. You need someone who knows about how to manage buildings, and EMPA, the building team, is one of the partners. And finally, the foundations for all of this is economics, and we have University of St. Gallen, which specializes in energy economics and are doing the sort of marketing aspect of this. Last slide, what is there, what are the questions we're trying to answer here? Basically, there's 4 basic themes. The first is economics. How much is this worth to the grid? That's what SwissGrid is trying to answer. And then the other 2 questions are technical. Can we use HVAC systems for big buildings or a large number of small loads to provide heat storage and reserve capacity for the electricity grid? And then finally, how can consumers be induced to take part in this? So what is the benefit for the grid? What is sort of the loss of welfare or loss of utility for the individual consumers? And then given that there's more benefit to the grid than loss of utility for the consumers, how can you entice consumers to actually participate in this scheme and take advantage of this? We also are hoping to have a validation at the end of the project. EMPA is building a building in their campus in Dübendorf, which has sort of open possibility for doing control on it, and we plan to try some of these algorithms on the building of EMPA at Dübendorf. And that's basically the end of my project.
So good afternoon. My name is Chris Moser, and I'm the coordinator for the project SHINE. So when you have renewable sources such as wind power and sun power, you need to have attached to it a storage mean to store the power when it's too much sun. For example, at noon in Germany, sometimes they have to shut down the photovoltaic panels because there's too much energy and not enough demand. So storage is essential. So this program here looks at the engineering aspect of generating hydrogen from sunlight. And we're taking an approach which is based on photovoltaics to generate a current, and that current is then used by an electrolyzer to produce hydrogen via electrolysis to produce the gas form of hydrogen. So it's hardly a new idea, okay? So if you look, there's a lot of work that has been done in the last 20 years in photovoltaics, in components, electrochemical components. So we don't want to redo that. So curiously, very little has been done into the system aspect. How do you combine photovoltaics and electrochemical components to make cost-effective hydrogen generators? And that's the topic where we're focusing. It's also good in Switzerland because we're experts, we're very good in photovoltaics with various groups, in materials with EMPA, and we also have good optics people here in Switzerland. So, let me tell you a little bit what we found out. So we made this analysis, and this is about the results. It's a bit surprising. So this is the IV curve of a photovoltaic cell, voltage versus current. And current hydrogen production is proportional to current. So now when you feed that into an electrolyzer of a certain size, if the size is large, so the area of the electrolyzer is large and comparable to the size of the absorber, of the light absorber, so what happens is that you have this load curve here, which is used by the electrolyzer, and the operating point is here at the intersection where you generate hydrogen, okay? When you look at the size or the costs of producing hydrogen, you are on that side here. The size of the electrolyzer is very large, so the catalyst costs a lot. So you're on this side here. Now if you take the opposite way, you shrink the electrolyzer size, you shrink the electrode size. So now you have more current density, you have less platinum, less catalyst, so it's less expensive, but then your operating point is not optimal. So you generate much less hydrogen than you could. So then your point comes out over here. So there's an optimal point. I think the take-home message that there's an optimal point of a size of an electrolyzer to match for production cost, which is not the maximum operation point in terms of efficiency. So if you look now, so we modeled this, and we took a case where there's a lot of work being done in this area, which is you take a photovoltaic panel, And let's say you cover one side with platinum, the other side with iridium oxide, you get an integrated electrolyzer directly. So the area of the charge of the PV is the same as the area of the electrolyzer. So then you see the cost is completely dominated by the catalyst. Okay? And if you look on the right side here, if you optimize by the method I've shown before, with the different sizes of the absorber and the electrolyzer, then you notice that the cost goes down and the catalyst of the electrodes doesn't matter, okay? Because you can shrink it to a point where the amount of catalyst is very little. So that was surprising to us, and so we just submit a paper with respect to that. So what's next? We can stop here and claim success, but it's not everything. By the way, it's already pretty good in terms of the cost that you can get from hydrogen from fossil fuels, and it's actually fairly good. So what's next? So what's next is we would gain even a higher cost advantage if we can limit the amount of photovoltaic surface. So you can do this by concentrating light. If you concentrate even by 10 times, you can reduce significantly even the cost. So that's what we try to find out now, a different way of generating, of concentrating light. And part of the project is to find different ways, novel ways of concentrating light. And this is one we're experimenting, where the light is actually, so I don't have time to go through this, but in the end, you have light coming this way, and then it's gathered at the edge of this waveguide over here. And this is a demonstrator, a proof of concept that it's actually working passively, so there's no mechanical tracker, so it's totally passive, and you can get 20 to 50 times concentration without trackers. So it could be cost effective, and therefore could limit the amount of PV. However, the bad part of it, when you concentrate light, you actually have a thermal problem, because PV panels are about 20% efficient, maximum 25. So 80% of the light of the energy is lost as heat. So you're going to heat up your panel. But since we have water, since we are using the feedstock is water to generate hydrogen, we can dunk that PV inside water. There's two cases. The left one is a 3-junction cell made by CSEM on which we deposited platinum. Light is concentrated, okay, on this area, and then we generate bubbles. So everything is inside water and cooled automatically by the water. The other way to do it is to actually have the 3-junction cell here to generate the right voltage, and just feed it with wires. So one is called wired versus integrated. There's a big debate in the community. Integrated is more elegant than wired, but both give the same result. Okay, and these are both working devices that are actually shown on the table. Okay, so last slide. So we're trying to model this even more than the first slide I've shown with the prices. This is a unified model with multi-physics. And the difference between the first model I've shown and this one is that this one integrates the heat problem with microfluidics to actually solve this heat generation by the PV efficiency. So it's done by a group with EPFL. So finally, this is my last slide. So what we're trying to do here is really taking a systems approach to optimize and find design rules to make practical solar hydrogen generators. One aspect is to develop novel type of concentrators, not very large concentration, 20 to 50. So really in the dead zone in terms of the concentrator that people do typically, which have 500 times concentration with junctions. Photovoltaics that have enough voltage to generate 1.5 to 2 volts to split water, and then microfluidics to manage the heat due to the concentration of the light. And finally, you want to make a demonstrator that's cost effective. Okay, thank you.
Okay, thank you very much for bearing with me for the last talk. My name is Andreas Burg from EPFL, and I'm replacing replacing Christian Piguet, who is the PI of the IcySoC project. I would like to use the next 5 minutes to give you an overview of the project and the challenges we are having. So IcySoC is a collaborative project between the CSEM, Christian Piguet, the ETHZ with Professor Benini, the EPFL with Professor Christian Enz and myself, and last but not least our industrial partner, EM Mara. Let me start by telling you a little bit about the motivation for the project. Today we have heard much about embedded devices and about devices for biomedical monitoring, environmental monitoring, and all kind of wearable devices, and those devices, they need to have computational capabilities. Now, recently the trend is shown on the bottom of the slide. Originally, computational devices were large, but then we managed to actually move more and more of the computations into the cloud, into big data centers, and to basically outsource the computations from measurement devices and thereby do complicated functionality even in mobility. Now, it turns out that this communication is not always cheap in terms of energy, and that means that more and more computations also have to be done on the platform, on the mobile and wearable platform itself, and therefore computational functionality needs to move back to the device. We need to have tiny devices that can actually do a few hundred mega operations or even giga operations with a battery that is very small and doesn't dominate the overall weight and size of the device. And therefore, building computationally efficient devices is a great challenge for many of the Nano-Tera projects that you have heard about today. Well, let me qualify this challenge, explain you this challenge a little bit better. We have heard partially about this topic also this morning when the plenary speaker, the keynote speakers were talking about the energy efficiency, for example, of the brain that is actually amazingly high. What we see here is actually a graph from IBM that shows the computational density versus the energy efficiency, and we see that with better technologies, of course, we have gained quite a bit in terms of energy efficiency in the last couple of years, but we still have a humongous gap, and of course this gap, depending on how you look at it, can be larger or smaller, but it is definitely, in any metric, it is by a few orders of, it is quite a few orders of magnitude, and therefore there's still a big step to go. So just in terms of raw computational power, where we would like to arrive is to achieve about 1 giga operation per milliwatt, which turns out to be a challenge where we are about a factor of 10 to 100 away today. Another problem that may not be so obvious is we're pretty good in building high-performance computers and can also work on energy efficiency, but a big challenge actually lies in building systems that are turn out to be energy efficient over a large operational range. That means they are not optimized for a particular operating point, but they are actually optimum in terms of energy per operation from a few tens of kilo operations up to a few giga operations per second, and in that entire range stay at the optimum energy efficiency. This means actually doing, needing a lot of energy when we need to work hard, but being frugal with energy if life is easy and we only need to do light work. And that's something that occurs often in many mobile applications where you're turning on a device and then do the hard work when it's actually needed. So what we are providing is a platform for many of these applications in the future. Let me tell you a little bit about the challenges in doing so. How do we build that? The starting point for our work is a platform that was developed at the University of Bologna and now at the ETHZ in Professor Benini's group, which is a multi-core platform that basically builds on many, many small components that are compiled together in a very flexible system that can be configured to always operate at the optimum operating point. And this is the platform from which we are starting, which we are augmenting by more efficient computational units and domain-specific accelerators that provide high energy efficiency for various applications. Let me go a little bit more into the details of these techniques very briefly. One of the main techniques that is used today to get energy efficiency is a technique called voltage scaling. That means we are reducing the operating voltage. That gives us better energy efficiency, but it also makes devices slower, and therefore it is more hard to get all the workload done in a certain time. It also involves challenges that, for example, at some point, as you're operating at very low operating voltages, modern process technologies tend to become unreliable and suffer a lot from variability. And therefore, there's a certain point where when you're trying to optimize the energy efficiency, reduce the voltage, where what happens in today's devices is that they basically shut down, they break down completely, they stop working. You can think of your cell phone, when the battery runs empty, it just shuts down and that's it. Even though there may be a little bit of battery left, but that's not enough to function, for the phone to function in the way that you're used to it. Now, the idea to solve this problem is a new computing paradigm that's known as approximate computing. The idea here is that we have many applications that don't always need a constant level of quality or a constant level of performance. Instead, you have quite a large range in quality that the user is ready to tolerate. And therefore, you have another area, another dimension where you can start doing a trade-off. When, for example, your cell phone becomes empty, it could go into a low power type of a survival mode and basically still provide a decent amount of quality to your applications. Still, the display would not be quite as clear, the animations wouldn't be quite as smooth, the voice wouldn't be quite as clear, but they would still function. And that's gives us another dimension in which we're going to work in this project, and what we're going to use to try to stretch out the point up to which we can go in terms of energy efficiency and provide devices for many of these applications. With this, I'm basically through with the explanation of the project. Thank you very much for the attention.
Thank you very much, Andreas, for the last presentation. So before leaving the floor to the question from the audience, I would like to ask you a general question that is a sort of summary of the common aspects of the project. If we talk about systems, I can realize that there are opposite trends. For instance, in power systems, historically, we moved from centralized energy conversion systems towards decentralized distributed generation. If we look at the computation systems, we moved from the era of PC computing to cloud computing, which is completely opposite. I guess somehow we can infer also the same trend at the device level when you talk about the optimization of a single subsystem or the optimization of the whole energy conversion system on its own. Now, can I ask you to give your opinion about which are the technological and scientific trends that justifies the move from centralized versus decentralized approaches and vice versa?
Just a first high-level comment on this. In power systems, indeed, it moved towards decentralized things, but I think the scope of the problem changed at the same time. So it used to be just control of the grid or regulation of the grid, regulation of generation, and the loads were doing their thing. Now the program became more ambitious and people look sort of more holistically at the whole system, even interaction between different energy carriers and how they can interplay against one another. And I think if one could do it in a centralized way, they would probably do it because you can, achieve possibly better performance this way. But the size and the scale is such that you can, for the time being, you have to live with decentralized solutions. And perhaps on the computing side, it's the opposite. You do it because you can. So you can move to more centralized architecture and get benefits in performance as opposed to having to live with decentralized solutions.
Maybe a short comment. So as we heard this morning, or the afternoon, actually, an important point is that at some point there was a big grid, for a big communication grid, like you have the grid in power systems, we have the communication infrastructure that is needed for computing systems, which was put into place at some point and thereby became available as a tool and immediately enabled this decentralized processing in the cloud. So,
with respect to fuel from sunlight, the purpose of generating fuel is that it can be transported. So decentralized by definition, you can use it in transport for fuel cells. But there are cases where actually it's on site. You have turbines that generate electricity and then the hydrogen is generated right there just to have a buffer for the grid. So it can be both. It's pretty flexible.
So let me go back to the part of the computing. So in that sense, you said that the system has gone to a more centralized scheme. The reason is actually mostly economic, I would say. So there are two different aspects here. So one is technology-wise, you observe that it's not an efficient use, for example, of servers that were always designed for high performance and so on. When they are underutilized from the energy viewpoint, they almost consume the same amount as they were fully utilized. So if you have a system that is not very often used, automatically you're still consuming the same. So if energy becomes expensive, you want to do as much as possible in the machine. So automatically, because you manage to get a good communication scheme, you see more and more in the companies, you have all the resources allocated in the same place to maximize the utilization of the very few servers, high performance ones that you have in the system. So that's the reason why you have that. So it's more an economic reason. So if you look at the ideal trend, what everybody would like to have, and I think I go back to what a little bit the trend of what we are seeing in the other aspect, which is on embedded systems. If you can manage to get some kind of energy proportionality that you want to have, the less effort you do, the less energy you consume, and you manage to get that from electronics, I think there is always a trade-off between centralized and distributed, and you will not be able to manage to get a full dominant in any of the two ways. So that's the main reason. I think right now we're in the centralized effort. It provides more resources, and you have a few places that can provide you these resources. But I hope that with the efforts we are doing, you get more linearly scaled, and then you will see there's a certain trend to decentralize again the resources, because it's very expensive to have centralized sources.
Yeah. If you think in terms of energy and production cost with the source of energy, very clearly the old source of energy, big power plants, will not be cost effective anymore against the new generation of photovoltaics. And this will create, in sunny countries, if you have some batteries, your photovoltaics, people will start to disconnect from the grid, and we will experience the phenomenon of grid defection, which means here there will be a tendency for people, like grid operators, that they cannot make profit anymore. They will raise the cost, we discard that at lunch, and then even more people will defect because it's too expensive to buy. So we will see kind of forced revolution in the field of the energy distribution. And here the answer is quite simple. It's much easier to make 1 million times the same solar panels than to make 5 nuclear power plants, where each case is special one. So very clearly here we go for a kind of dichotomic system, on which a lot of distributed generation, and in some part of the world where you have no other choice, there will still remain some big parts.
So I'd like to address this question by a second question. This is maybe the first time we are addressing a topic which is energy. And in this field of energy, there is top-down approach where people try to provide energy for people, and then as well we have people that will receive this energy. For the first time, people start by themselves to try to improve the way of consuming less. So it means that in this kind of debate, we have this additional layer, which is society. And we cannot today speak energy without speaking about the impact of what you are doing. If somewhere is a renewable energy with a zero footprint, go ahead, do what you want with the technology. If somewhere we have to share this one with something else and we would like to manage, we have to move the question to the society, to the origin of the debate, which is humanity, footprint, as well as energy. If this one is top-down or bottom-up, there is a mid of them where the technology should converge to meet the human demand.
Yes, that we have time for questions from the audience. So please.
There is a number of projects where addressing extremely important goals, but at the same time goals that are also addressed by much more powerful identities. I was thinking about the optimization of power in the data center. Obviously, Google is doing that with the power of Google. If you're trying to compete on the market of solar photovoltaic, it's of course tough because there are big players there. In general, how do you sort of, and of course it doesn't mean that projects are doomed because you can always go away, but how do you address this issue of being in a field where there are basically very big players that have really means, and how do you sort of distinguish yourselves from that?
I'll just start with solar. Of course, there are big players, but I think there are still a few companies in Switzerland that are major players, like Delivery Equipment for production line worldwide, like ABB producing inverters with research center in Switzerland. So there is a lot of knowledge and product export, and a lot of companies of the major one rely on us. And we have a lot of new things. We have patents. So people cannot go around Switzerland so easily. So we're still there, but of course it has become more major market as compared to 5 years ago, and we have just to fight. But this is a nice fight.
Yeah, from the side of data centers, I think it's a very interesting question. So already when we have the first presentation of this type of project to large companies, they always say, well, we are doing it already. So the answer I would say here, we are not targeting to compete with the way Google designs their data centers, because that is not the target of the project, in the sense that if you want to design a very large data center, you have extremely large IT equipment and company that are able to do that, you will not have a problem. But typically this will be designed for extremely precise or one type of technology and one type of problem. That is not what we are targeting here. We're targeting here the other side. So I would say middle range, but I would not classify Credit Suisse as a middle range size company. But I still have to say that they have, from the IT perspective with respect to Google and so on, they are still not in the same league. So in that sense, there's a large number of companies in Switzerland as well, where we have a lot of medium-sized companies and small-sized companies that they still need to use IT resources. So they are in need to have a scalable technology, not in the sense of hiring 150 engineers to help you to design a data center, but really have 5 engineers that will automate the whole process. And for a small type of a scale, you can actually do the whole design of your infrastructure. In that sense, it doesn't mean that we can do it alone. And I would like to point out that when we define the project, the first question that we had is, well, how are you going to bring these ideas to something that is usable in the market? And for that, we have had in the consortium long discussions of who should be involved, and we have realized that in the end, you need to make quite a large consortium because you need to integrate people working in companies on all these layers. So we have the assessment coming from Credit Suisse and BrainSurf as users, and we have also a large company provider, which is Eaton, that is not really a minor enterprise. It's a large corporation worldwide, but they're still having a small portion on this area of large data center, but they are targeting small companies. And there they can have a lot of small requirements, and it will be surprising to see that if you try to apply Google technologies for just these companies, have nothing to do. They will never actually work. So that's one of the main reason differentiation comes.
I think it's a very good question, actually. We actually thought about this. You know, the energy is either if you're a very big player, you have no chance. So you know, when you do it at the university level, what do you do? So we looked at it, at least for the sun to fuel, at a system level. So at the system level, there hasn't been a lot of work because universities tend to not work on system level. It's mainly component and basic science. Corporations, it's too expensive, so they haven't really paid attention to it. So there was a sort of a little opening there in terms of looking at the system level, agnostic about the technology, looking at every type of photovoltaics or electrochemical systems, and then finding some design rules that can be used. I think that was sort of the point of the project, but I think that's a very good point that you raised.
Perhaps I can say something on the sort of more grid and demand response side. In my biased view, I think there's clearly established players and people who know what they're doing in this area, and they're the people we turn to for information and advice. But on the sort of next generation systems, there's a lot of discussion and there's no clear consensus yet, and there's a lot of conceptual work that needs to be done. Also, you know, what is feasible, what is economically viable, and so on. And we're in a lucky situation now that we are at this stage, and universities have a lot to offer to this. And there are concepts, there's no clear business models for many of these. Google is sort of moving into the picture by the purchase of Nest recently, but there's really no clear view, as far as I can tell, what exactly they're going to do with this. In Switzerland, Swisscom is starting something, but it's a very much startup operation. So it's actually a very good time to be involved in the research to be able to set down the foundations for the next generation system.
Thank you for posing this interesting question. Other questions from the audience? For our panelists? Well, I have a very last one. Talking about energy, in general, there are two points that we try to use to drive our research. One is efficiency, and the other one is power or energy density. how these two quantities are important in shaping devices, systems, and algorithms of your research activities.
In fact, it's a very good question because especially in my field, people talk a lot about energy and energy efficiency, and I have used the word, but indeed, in many cases, power is actually the other very important aspect. For example, if you think about sources that can only deliver a certain amount of power, you're not necessarily caring about the energy efficiency itself. In system where you have harvesting and so on, and the optimization criteria, they are not always quite the same. And the systems you're building are not always quite the same, so they actually need a little bit differentiated view. So
well, one point about the efficiency, on our analysis, it looks like the operating point to make hydrogen is not the most efficient point. To make cost-effective hydrogen is not actually the most efficient point. So you're actually wasting something. Unless you have DC-DC converters that are really cheap and efficient, we are off. The optimal point is not the most efficient point in terms of their generation, which is a bit surprising.
From the actually larger scale, if we go back to your question, how much do I care about power and efficiency versus really how much is the overall on rates that I can save? In reality, there are two intertwined problems. In fact, you can actually spend a lot of power, which is very often the case because today computer electronics for data centers and still high performance servers, you will not be able to really make them consume very little amount of power. What you can do very effectively, and that's one of the key aspects in the project, you can recover a significant amount of that. So right now, you hear very often still a lot of questions about how much energy I'm burning on just cooling the infrastructure or not recovering. So a very important aspect, and I think that you can actually take into play when you make these calculations of the energy I spend, is not just the initial expenditure on the servers, for example, is how much I can recover from that. So very often, a large interest of the main partners that we have here, for example, BrainServe and also Eaton is, well, they know that they will not be able to redesign the server from scratch in 3 years, but having what we have, what are the energy efficiency that we can get, if we take into account how much we can recover from these sources to put it actually in the system for power supply on the different grids and stuff like that surrounded. So in fact, I think we can generalize the question is how much would I spend if I manage to recover a certain percentage and what I get in the end as a final outcome. And I think there we can do quite a lot of things even with what we have today.
I just give 2 orders of magnitude. It depends so much on the problem you address. You know that we get in Switzerland, in Ballif especially, 1 barrel of oil, 154 liters of oil per square meter of solar energy per year. So 1 barrel of oil is a huge amount. So even for data center, we have a lot. And but if you have just a watch and you wear a coat like this, then your watch would get the equivalent of 1 centiliter or even 1 milliliter of oil per year. So depending on the application you consider, you have either a lot or not so much, and then you need to be very efficient.
I guess it's exactly the same answer. There is a time in between the energy and power. If you can schedule time and to predict in the demand side, you know exactly at what time you can dispatch power. You handle better the energy, and it means that the hot topic still the saving of the energy somewhere. So finding the way to store energy, it's still the big challenge where nobody's, I guess, here is working on it.
So I would like to thank all the panelists for their nice contributions.